as Charles mentioned, my name is Tom Teets. I'm the executive director of the California Nevada Cement Association. Like Charles Association, we're here to be a resource for you. And we are so proud to be able to put on the 18th annual Nevada Infrastructure Concrete Conference without a hitch. We're moving forward with full steam, even if we're virtual. So what we've done again is I feel like we've put together a very dynamic program. We've got an excellent group that envisions the topics and speakers for each year. And it's my pleasure to introduce our first speaker in the pavements module that we'll cover this morning. I want to mention too that after lunch, we'll go into materials, and you won't want to miss that either. But in introducing Tyler Lay, he's been very good at giving me a list of about this many things to talk about this morning to introduce him. But instead of doing that, I just want to say that Tyler, I view him as kind of a rock star when it comes to the concrete industry. If you have not visited his YouTube site, you have to do it. He has so much energy and enthusiasm and knowledge about concrete. I sure wish I had him as my professor when I was at school. The little secret is one of my concrete classes I had in undergraduate was my least favorite class of all. It was very difficult and boring. But as you'll see here, Tyler is none of those things. He is going to be talking to us about optimizing concrete mixtures. And with that, I'm just going to hand it right over to Tyler. We're so glad to have you here this morning.
Hey, thank you so much. I'm so sad that I can't be there, in person. I think a buffet lunch or a buffet breakfast sounds totally amazing right now. My name's Tyler Lay. I'm a professor at Oklahoma State University, and I want to say first and foremost, a big thanks to Dan Cook and Nick Cedar. These are folks that did a lot of the research that I'm going to share with you today. But I'm going to not talk about just pavements today. I'm talking about all concrete. So, yes, concrete. So let's get started. So I want to acknowledge Oklahoma DOT, Dick Gaynor, Jim Shilstone Sr. These are people that came before me. These are people that built amazing, did great things of our knowledge of concrete, and I'm trying to build on top of their shoulders, and that's always fun. Also, Tom Van Dam, Clay, Megan, thank you for having me today. Thank you for having me. I wish I could be there in person, but this is the next best thing. So what am I all about? I believe concrete is the greatest material on the planet, and I will battle anyone that says differently. I want to make concrete easier to construct, more durable, lower cost, more sustainable. That's my mantra. That's what I get up every single day and say. And I help build people and tools to help make the concrete industry better. I'm going to be talking about mixed design today and the importance of aggregate gradation. Yeah, the rocks and the sand. Talk a lot about that today. And something called the tarantula curve. It's totally going to be awesome. I hope you stick around and check it out. So what is the most important property of concrete? Got any ideas? Is it workability? Is it durability? Is it economy? Is it strength? What is it? I know. Every project's got some things that they want differently. But of these four, which one is the most important? Which one that if you don't have this, you don't have any of the others? And the answer is workability. Because if you don't have workable concrete, you can't place it. You can't consolidate it. You can't finish it. You can't even get strength. No one's going to pay you for it because you can't even do what you're supposed to do with it. That's why workability is so important. But I'm going to take just a second and talk about the other items here: durability, economy, and strength. But how do you design concrete mixtures? Well, is it as simple as rock, sand, cement, and water? It was a long time ago, but we've learned so much lately. Durability. If you want durable concrete, you need to pay attention to your water to cement ratio, the SCMs that you're using, like fly ash, like natural pozzolan, slag, how much air content you have. If you want strength, it's about water to cement ratio and air. Cement is not listed. I like cement. I'm a fan, but cement does not equal strength. Water to cement ratio equals strength. Economy. That's where cement comes in. Using local aggregates, minimizing admixture dosages, all of these things that contribute to the cost of our concrete. And these are things you can look at. But how do you design for workability? I mean, it seems impossible. Sometimes we're slip forming concrete. Sometimes we're placing with a truck. Sometimes we're pumping it. Sometimes we have to finish it. How do we do this? It seems overwhelming. But every single mixture has a different set of requirements. And I'm going to show you some of the secrets of concrete today. I'm going to show you some ways to design for all these things and do it economically and get great concrete. To do this, you can control your paste content. That's the water and the binder. You can control admixtures, and then you can control your aggregates. Now, we're going to be focusing heavily on aggregates. Why? Well, aggregates make up about 75% of the volume of concrete. 75% of the volume of concrete is rock and sand. That means if you ever hope to get control over the quality of your concrete, you better understand your aggregates and what they're all about. But do aggregates really matter? I mean, I say they matter, but come on, do they really matter? Well, I'm going to show you some results coming up from a mix design that on a piece of paper every single mix looks the same. Every single mix has the same amount of coarse aggregate, that's the rocks, sand, right? Same amount of cement, same amount of fly ash, same amount of water, but each one has a different gradation. What? That's like the particle size distribution. What we're used to talking about gradation, looking at something like this, where you have a sieve number down here and you have the percent passing, and everyone sees these S-shaped curves on every submittal you get, and they're like, yep, next, yep, next, yep, next. They just skip all those. Guess what? They're crazy, crazy important because they're the difference. Those S-shaped curves are the difference between what I'm showing you on the screen right now. If you get everything right, if you know what you're doing, it is going to be amazing. If you don't have the right amount of fine sand in your mix, oh my gosh, look at this. Like this is after the slump is pulled up, it falls apart, right? It's got a 5-inch slump, but it's not a 5-inch slump that I would want to pour with. If you have too much fine sand, it gets very, very stiff. Too much intermediate, it gets stiff. Too much coarse aggregate, you can see the rock trying to like come out of the concrete. Again, that's not what we want, but if we know what we're doing, we can get it just right. Now, if you go to finish the concrete, that's where you try to make it smooth. You know, again, if you don't have enough fine sand, it looks like this, a bunch of paste covering rocks. That is not what we want. If you have too much fine sand, oh my gosh, it's hairy and yucky and it's just so hard to finish. Too much coarse aggregate, you can see it kind of coming out of the mix. Too much intermediate, again, it's coming out of the mix, but if we get it just right, oh baby, it's amazing. And I'm going to help you today get it just right every time with less cement and fly ash and water, less paste, and save you money and get better concrete. So why would you do this? Well, we can reduce costs. We can improve our strength. We can improve our durability. We can improve our sustainability. We can get control over our mixtures. Yes, this is awesome. Right? So let's talk about this research we've done. Well, at Oklahoma State University, we used a whole suite of tests. We looked at over 700 different concrete mixtures, 13 different coarse aggregates, a whole ton of sands. We looked from slip form paving all the way up to pumpable, flowable concrete, from slumps like 0 inches to slumps like 8 inches, like flowing water concrete, right? We looked at it all and we summarized everything into a simple tool. Now, I'm going to use some tests to evaluate this. And these tests are going to tell us about real workability. How do you place, drag, pump, vibrate, and finish? And everything I'm going to tell you about today is on this website, tarantulacurve.com. It's my gift to you, tarantulacurve.com. It's got Excel sheets, it's got reports, it's got videos, it's got all kinds of stuff. Tarantulacurve.com. Oh yeah, it's all free. We're going to look at all of these tests, slump, something called the box test, rheometers, visual test, a float test. We have our own pump. Yes, our own pump. And we're going to look at pumping concrete as well. We'll start out with the float test. The float test tells you how you can finish the concrete. What you do is you place concrete in 3 foot by 2 foot by 3 inch deep forms. You fill them up, and you strike it off quickly. You don't saw it, you just strike it off to make it even. Then you're going to come in and create 3 1-inch diameter and 1-inch deep holes. We're going to come over with a bowl float and back and forth at a fixed angle over the surface. And we're going to say, how many passes does it take to close the 3 holes and make it smooth? Kind of confused? Well, let's look at some pictures. Here we go. Fill up the forms, strike it off. Template comes in. There you go. Put in this 1-inch hole. Why would you do this? Well, when I was a contractor in the past, many moons ago, sometimes when you strike the concrete, you pluck aggregate out. Whose job is it to fill those holes in? The finisher. So we want to know how easy it is to fill those holes as well as making a smooth surface. So here comes our float. It's been trimmed. It only rides on the concrete, not on the forms. It has a yoke in the back, so it's at a fixed angle. It moves back and forth. I'll tell you a secret. We actually have marks on the side and a metronome drum machine, so we can move forward and back at a very, very uniform pace. And what we see, how many passes does it take to close the holes and make it smooth on top? What am I talking about? Here we go. Here's a mix. After 4 passes, holes are closed. 6 is kind of like our actual breakover point. Here's a mixture when it comes to texture. We don't need perfection. We don't need that here. If we get to a 2, a visual ranking of 2, we are happy. That's 10 to 30% overall surface voids. And we measure how many passes does it take to reach that level. Next, we went on and said, let's pump this concrete and let's see how it actually performed. And we are so blessed to have our own concrete pump at Oklahoma State University. I believe in doing things that are real. And so we can conceptualize stuff, but let's really pump it. So when you go to pump concrete, sometimes the pressures can just be too high. It's very, very hard to get the concrete to move within the pipe. Sometimes the concrete can start to segregate. I'll show you examples of that coming up. That's scary, dangerous. Run for the hills, all right? And we should design our concrete mixtures so that doesn't happen, because that will hurt you big time when it comes to pumping. So we set up a whole pipe network like this. It's like a concrete roller coaster. We dump the concrete in here. It goes down, over, back, down, over, back. I would love to be in the roller coaster someday, but I just get to measure the roller coaster right now. And we have pressure points at each thing, where we have these pressure gauges that we actually measure the pressure here, 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 here at point 1, 2, 3, and 4. And it looks something like this. They have a buffer chamber at the top. That is an oil-filled chamber. And we have this oil pressure measuring gauge at the back. We have this rubber membrane that's up here at the top. So you screw this in. We've drilled a hole here, welded a nut on the end, screw this in. So as it's pumping, it pushes down that membrane, which pushes the oil in the buffer chamber, which we can measure. Hey, guess what? If you put the GE pressure sensor right in the concrete, it lasts exactly 30 seconds. I've done it twice because I wasn't smart enough the first time to figure out that it broke every time. The data looks something like this. As the pump starts to fire, as the piston starts to move, there's a certain amount of pressure that builds up in the concrete till it does move, till it breaks that friction on the side, and then it starts to flow through the pipe. So we can see this top, this batter. Look at that. Isn't that sexy? I think it looks really sexy. Here's a high pressure, lower pressure. Yeah, I told you I'm a freak. But if you get concrete mixtures, that's a good looking pump. That's a good looking pressure cycle. If you get mixtures that actually segregate, where the rock goes one way and the paste goes another way, I know you've seen them. I know you've seen them if you've been around concrete. This is what happens when you try to pump that. It starts to segregate in the line. It gets scary, it gets jagged, and these pressures are about 3 or 4 times higher than what they were before. What's the difference? The size of the aggregate and the distribution. Now, some people like to talk about cement content. Does cement content affect pumping? Oh, yeah, we can dial that in. When you have not enough pressure, not enough cement, 5.5 sacks of actual total binder, we can't pump the concrete. Once we got up to 6 sacks, much, much easier to pump. Once we go to 6.5 sacks, again, much, much easier to pump. So we can quantify stuff that you've known in your life, you've experienced. We can get real life quantifications. How does sand impact pumping? We can quantify it. We use something called fine sand. And actually, as your fine sand content goes up, I'll teach you what that is coming up, it gets easier to pump. Oh, baby, it's awesome. So how about paving? Because that's what you invited me to here to talk about, was talk about paving and what it's all about. We have done tons of paving with this work, where we've actually gone in the field. We've designed this mix. It looks scary. It looks bony. It looks like there's too much coarse aggregate in it. But if you know what you're doing, once it goes through the paver and vibrates, oh man, it looks like this. That's the same mix, right? And paving is a unique beast because you want the concrete to be workable, but not too workable. You want it to be workable enough that the vibrators can consolidate it, but you don't want it to be so workable that it doesn't hold an edge. So you need this boundary. You need to understand it needs to be stiff enough, cohesive enough to hold together, but not too flowable. And so how do you figure that out? Well, we started to think about, how does a paver work? How does a paver really consolidate the concrete? And it's all about the vibrator. It's all about, how does that concrete respond to the vibration? So we said, how could we simulate that? Well, we wanted a simple test that could measure this response to vibration, measure this filling ability of the grout, and also the ability of the slip form concrete to hold an edge, to be cohesive. This kind of two edges that I talked about before. And the slump test, although it's totally amazing for certain things, is not amazing for this. So we came up with a different test. It's called the box test. Now, I'm thankful to say that the box test is now an AASHTO standard. Wow, go check it out if you want to. It is a 12-inch by 12-inch by 12-inch box held together by these very expensive pipe clamps. $20 from Lowe's. Unless you're in Hawaii. When I gave this talk there, it was $40 because I went and checked. $40 in Hawaii, $20 in Nevada, pipe clamps to hold it together. Now, this box are two L's, okay? So it's an open top and an open bottom. We're going to fill that box full of 9.5 inches of unconsolidated concrete, 9.5 inches. We're going to take a 1-inch Stinger vibrator, not a paving vibrator, a 1-inch Stinger vibrator, and we're going to turn it on, take it down for a 3 count, take it out for a 3 count, and then we're going to immediately take the pipe clamps off, take the edges of the box off, and we're going to look. What's it look like? Does it have honeycombing? Does it have any edge slumping? Because those are the two boundaries. If it's got honeycombing, that means it didn't respond to the vibration. If it's got edge slumping, that means it's not cohesive enough to hold together. We did tons and tons of tests with this, tons of field validation with this. And here's how it looks. There's the concrete. There's the vibrator. There's where it goes in. You can see it's consolidated it. You can see the sphere of influence of the vibrator has actually gone out and consolidated the concrete. And the size of the vibrator and the size of the concrete is actually sized, or decided, based on what a paver, the amount of energy that a paver would put into a typical cubic foot of concrete going at a typical speed. But after you take it off, you get this, a beautiful concrete brownie. Isn't that amazing? Unbelievable. What I love most about this concrete brownie is that there are no huge honeycombing surface voids, because we use a visual ranking scale between 1 to 4, kind of similar to the float test. We don't want 4. We don't want 3. We are plenty happy with 2. And 1 is great, but we're not building Swiss watches. We're building concrete pavements here. And so 2 is just great, 10 to 30% overall surface voids. We also look at edge slumping. We can go around and compare with a straight edge. Does that concrete hold an edge immediately? This is like right after mixing, run this test, or if you want to run it 3 hours after mixing, you can run the test. It doesn't matter. Does it hold an edge? Does it respond to vibration? Here it is, right? You can see this one leaning over. That's not good. You want these nice, crisp edges. That's what it's all about. So in summary, the box test examines this window of workability. This is helpful when you're designing mixes, when you're trial batching, when you're troubleshooting. It's like having a miniature paver. We looked at over 650, close to 700 mixtures, tons of different materials, low workability, high workability, different water cement ratios, different paste contents, different water mixtures, different admixtures, over $1 million in research, ladies and gentlemen. And we summarized everything you need to know on this next page. This is the tarantula curve. Now, it's got the sieve number down here. This is the sieve. This is the size of the aggregate down here. And this is the percent retained, not the percent passing, the percent retained. And you want to be within these boundaries, but there are 2 other checks. And we'll talk all about this coming up. Now, why is it called the tarantula curve? It's because I think it looks like a tarantula. You see a tarantula? Leg, body. And I came up with it. Well, me and my team did. So we can name it whatever we want. If we want to call it the Batman curve, we can call it the Batman curve. We didn't. We call it the tarantula curve. That's what it is. You can find more information again at tarantulacurve.com or tylerlay.com/tarantula videos. It's not about spiders, ladies and gentlemen. It's about concrete. So we take stuff that looks like this. Gradations, your typical S-shaped curves you've seen with percent passing, the ones that everyone turns in that no one pays attention to. And we turn it, we have spreadsheets that do this for free for you, into this, a percent retained graph. Takes this, turns it into this, and says when I have sand, there's actually a lot of number 50 and then it goes down. When I have an intermediate, there's a lot of number 4 and then it goes down and down. When I have a coarse aggregate, there's a lot of 3/4 and then it goes down and down. I realize yours are going to look different than mine. That's fine. You use your stuff. And then what you do is based on the amount of coarse, intermediate, and sand you use, you get this thing called the combined gradation. And that is what goes in the tarantula curve. Let me show you what I'm talking about. Let's step through every one of these boundaries, and I'll try to prove to you why it's important. So here's the plan. We're going to use workability to look at how gradation impacts our performance. So as we change gradation, we can directly see how this impacted each one of these tests. We use all of these tests to give them a ranking, and we're going to try to find limits, the oh no limits, right, when bad things start to happen. So let's start out with this one. So this is this percent retained chart. So this is like a waterbed. I'm from Oklahoma. We got waterbeds here. I don't know if you have them there or not, but in a waterbed, if you push down one place, what has to happen? It goes up someplace else. That's what happens here. Everything has to total to 100%. So if I go down in one place, or decreasing my 57 stone, if you're a concrete person, then I'm going to increase my number 8 or my intermediate material. And I have a poor workability at the beginning, right? So if I do this a little bit, it gets better, and then it gets good, and it's good, and then it's still good, and oh, it's not as good, and then it's poor again. And it's still poor. This is important. This is critical. I know you've seen this in your life. Too much of something is bad. Too little of something is bad. The right amount, that's what we're looking for. Concrete's the same way. If you have too much of any one sieve size, you're going to have poor performance. If you have too much, as we start to get poor down here, we get too much of a sieve size over here. And this teeter-totter, this kind of good in the middle, too high, too low, going to be a problem. You're going to see this trend over and over and over again. Here's what happened in the slump. Moderate amount, right in the middle, everything was great. Too much intermediate, it was too stiff. Too much coarse, it looks something like this. We looked at our finishing as well. Right in the middle, boom, that's the stuff you want. Excessive coarse, the coarse is like coming out of the mixture. Excessive intermediate, it's coming out, it's starting to segregate. It's not a good thing. So as long as the percent retained was not more than this 20% boundary, good things happen. You were in good place. This boundary was everything. But as soon as one started to go above the limit, poor performance started to happen, and you started to see an increase in segregation and a loss in workability. Let's talk about sand for a second. Now, we usually use a term called the finest modules, or the FM. It's developed by Duff Abrams, one of my concrete heroes. If he's not your concrete hero, something's wrong with you. He's amazing. 1916, he came up with this finest modulus, and it takes an entire sand gradation curve and expresses it as a single number. Now, can you ever express anything complicated by a single number? As engineers, we try heavily, and I think we fail over and over and over again, especially when things get more complex. Ladies and gentlemen, if you're dealing with a manufactured or blended sand, finest modulus means nothing. And everything you've been taught in the textbooks means nothing. We just completed a huge study on blended sands. I'll tell you some of the high points at the end of this, so start paying attention. What am I talking about? If I have something called something like this is percent retained, and this is the sieve number. Now, this finest modulus, this number that the concrete industry lives and dies by when it comes to sand, all three of these have a finest modulus of 2.54. All three of them. And look, the curves are pretty similar to one another. These are all natural sands. When you start to go to blended sands, they look like this. These are real sands, ladies and gentlemen. Real stuff. All of three of these have the exact same finest modulus, but very different gradation. Finest modulus was great in the past. It doesn't work anymore. It's when you start to get these more complex sand combination. So why don't we do this? Why with our coarse aggregate, we have larger stone and intermediate stone. Why don't we do this with our sands? Well, here's our fine aggregate, right? And we're going to try to do that. We're going to try to talk about coarse sand and fine sand. This is important. You should pay attention, especially if you're going to deal with blended sands. Pay attention, right? Right in this region. This material, this 8 and 16, it's critical for form, for finishing, and also for cohesion. So to prove this, we did something where we took every textbook that's out there, and if you look at optimized graded concrete, they will tell you that the best gradation on the planet is this one, this bell-shaped curve. We sieved it, and guess what? It's not the best. It was horrible. And this one over here, which a lot of people would call gap graded, okay, that terminology needs to go away. But they call this gap graded. It was awesome. It smoked this pour mixture. What am I talking about? If you go to finish this idealized, supposedly perfect mixture, this is what it looked like before finishing. This is after 8 passes. It took something like 16 passes going over and over and over again. This is why people add water to the surface of concrete. This is why people cuss about mix designs, all right? It's because of poor finishing and poor consolidation problems. So to understand this, we started to take out and put back, better understand what was going on. The same teeter-totter effect that I told you about before. And if you have too much of this sand, it was poor. But if you have too little of the sand, it is also poor. Same trend I told you was going to happen before. So the poor finishability in the float test, you can see 0 passes looks something like this. After 8 passes, that's about where most mixes should be. And this is after 18 passes, we finally got it smooth. That is not good. That's extra effort. That's not what we want. How to fix that? Just reduce the amount of 8 and 16, and that goes away. If you have too little, you can get poor cohesion. What am I talking about? All the coarse aggregate is here. Very, very little, mainly paste out here. That's not good. That's not what we want. That's called segregation. This is also having too little of these materials can cause segregation. So again, this we set these certain limits, right? And the tarantula curve helps you with those limits coming up. So how do I check this? Well, with the coarse, that was super easy. Coarse aggregate was super easy. Did you go above or not this boundary? But coarse sand, you still have the boundary, but now you do another calculation. It's not a very hard calculation, but you say, how much number 8, how much number 16, how much number 30 do I have? Literally add it up, 8, 16, and 30. And if that number is greater than 15%, boom, you're good. So that was 25.6, and that goes up in our oval, ladies and gentlemen. And if that's greater than 15%, boom, we're good. That's just what I said. Let's go into our fine sand. This is the smaller material from the number 30 and below. We're going to do the same type of thing that I've just been showing you. Here is when we have too much sand. This is unusable. We're going to push this down, and then we're going to move these up. Reduce sand, increase the amount of intermediate and coarse aggregate. Look at that. It's poor. It's good. It's good. It's still good. Then it gets moderate. Then it gets poor. Then it gets unusable. Ugh. The same things are happening. Too much sand, it's like a hairy mass. Not enough sand, it's like you're got paste surrounding rock. Right in the middle, it's great. Ladies and gentlemen, all of these have the same cement content. All of these have the same fly ash, water. All of them are the same. The only difference, the size distribution. That's the only thing. Here we go. Excessive sand, sufficient sand, deficient sand. You can see it with your own eyes. Here's this segregation I told you about before. This is really extreme segregation. A lot of coarse, a lot of paste over here. This basically, we found these ranges of sand that as long as you're between about 25 and 40% sand, you were good. Everything was great. And as soon as you start to get too little, things were a problem, and too much, things were a problem. So how do I check fine sand? Kind of similar to to the mid-range sand or the coarse sand. Is it within the boundary? That's question number 1. Number 2, how much number 30, 50, 100, and 200 do I have in my mix? I total those up. I get 28%. Is that right? Well, that's going to depend. I go up and look inside the box and see what I need. If I'm using a flowable concrete, this is a pumped concrete. This is something I'm going to finish. This is something that I want more than 3 inches of slump. Then I'm going to want a fine sand content between 25 and 40%. If I'm doing slip forming, I want between 24 and 34%. Slip forming needs more cohesion, so therefore you do not have as much fine sand. Flowable needs more finishability. That's why it needs or would like to have more of that fine sand inside of it, so we can better understand and quantify this stuff. This, I know, I hope it doesn't seem too complicated, There are Excel documents that make this easy. People are using this. Let me tell you about it. But how about other mixture procedures that are out there, like the Power 45 or the coarseness factor? Maybe you've heard about those. Power 45 chart's pretty easy to use. We have the percent passing you plot over here versus the log of the sieve number down here. And you get this supposed maximum density line, right? It was developed for concrete, but the asphalt world uses it right now. And the idea is to put your mixture along that maximum density line. But all of these red lines here, I made them. I made them and I measured them and I tested them, and they had very poor workability. The green ones here had moderate workability. You can see, are they getting closer to the line? I don't know. But all of these all had good workability, as in outstanding, as in you would love them, I promise you. And they're not all close to that black line. And guess what? This red line I'm showing you, that's got poor workability. It's right in the middle of all the good ones. Can you tell any difference? I can't. The Power 45 is cool. It shows some good stuff. I think it's theoretically neat, but it's complicated and doesn't always seem to work. And the tarantula curve makes this a lot easier. Tarantula curve also pays attention to your fine and coarse sand content. Then there's the coarseness factor, or the Shillstone chart, where you plot the workability factor over here, which has to do with the amount of sand you have and the amount of cement you have, and the coarseness factor down here, which has to do with the amount of coarse aggregate you have and intermediate aggregate you have. And the idea is you want to be in this center box. That's the concept. We made these mixtures all over the place, and everything here that's black is good, right? And everything that's red was horrible. You would hate it. And look at these two. They're right next to one another. One you would hate and one you would love. And here's why. The Shillstone chart is cool. It knew lots of neat stuff, but there's things that it missed. This has a poor workability. This has a good workability. And it straight up missed it because the Shillstone chart doesn't tell you how much can be on each sieve. It just tells you in general coarse versus intermediate. So in summary, the Power 45, the coarseness factor 818, they were a great start, but they're not complete. This tarantula curve is simple. States are using it. I get emails every day from people. I get I get little videos from people showing me with them using the box test and doing this stuff. People are loving it, giving us great feedback on it. But here's a real case study. Minnesota DOT wanted to optimize grade their concrete. This is 1996 and 1998. They didn't know anything. They'd never done it before. And they just tried. They just said, hey, let's try to do it. Let's use some of the tools, the Power 45, the Shillstone, the stuff that I showed you before. And this is showing the tarantula curve outline, and this is showing their gradations. And not very many of them were within the tarantula curve, and the performance between 1996 and 1998 for their pavements was pretty hideous, pretty horrible. By 2009, because they started to pay an incentive, they started to encourage people kept trying. 87% of their mixtures fell within the boundaries of the tarantula curve. By 2010, 98% of their mixtures fell within the boundaries of the tarantula curve. Now, ladies and gentlemen, why this is so interesting and cool is in 2010, the tarantula curve didn't exist. We hadn't even started the research in 2010. These contractors are not stupid people. They're not going to use what doesn't work. They are going to use what does work, and especially if they're paid an incentive. Especially if you give them a reason to try. They're going to try and try hard. And they found something themselves through iteration that is very similar to what I found in my lab. They didn't find all the boundaries. They didn't have all the science we did and all the testing we did. But I think this is amazing. Something in the field can validate something that's going on in the lab. And if you look at the percentage of mixtures that are within the tarantula, it goes up and up and up and up. And if you look at their smoothness of their pavements, as they got more and more mixtures within the tarantula curve, their smoothnesses, their IRIs got better and better and better. So Minnesota contractors are having good success with this. They're doing this with trial and error. They have no knowledge of the tarantula curve. And as more mixtures entered the tarantula, smoothness got better. I got similar data to this for Iowa and Michigan, if you don't believe it. So how in the world do I get a mixture inside the tarantula curve? Well, usually you need 3 different aggregates, usually. Why? Because you need levers. If your course is out, you pull the other 2 levers to get you back in. If you don't understand what I'm talking about, I'll show you coming up in just some images. But this is what it's all about, having options. So for example, if I have too much coarse here and I have a poor mixture, I'm going to decrease my coarse, increase my intermediate. Now, does it have to be intermediate? No. I could decrease or increase my sand if that's what I need to do to make it work. It's whatever you need to make it work. Do my curves have to fit within the tarantula? No, of course not. But you're going to need more paste. If you're ever using 700 pounds per cubic yard of concrete, you might want to look at your gradations when it comes to paving. This usually means more cost, greater risk for cracking, things that everyone wants to avoid. Do aggregate shapes matter? Yes, they do. They do. And I'll tell you how. This one, and this one were all mixed at the exact same gradation, and they used very different water reducer dosage to get a certain amount of slump. This one needed none. This one needed 6.9. Now, why? See how these are flat? See how these are elongated? That's not your friend. How do you measure this? Well, we have a test out there, the ASTM D4791 test. It measures the long dimension to the short dimension. It looks something like this. Your minimum dimension to your long dimension. If less than 15% of your particles meet this 1:3 ratio, boom, that's what you want. That's what it's about. Do my aggregates have to meet this? No. But again, you're going to need more paste to make this work. So, hey, does the tarantula curve work with man sand? I know you've got some of that blended sands. Of course it does, right? And there's a tweak, though. I wish I had more time to explain this. Maybe you can reach out to me and we can talk more about this. You're going to change these limits by 2%. Up by 2% if you have man sand. It's that simple, ladies and gentlemen. Say, how in the world can it be that simple? Oh, invite me back, and I would love to tell you how simple it is. Why in the world would you do this? Because you can simultaneously reduce your cost, improve your strength, improve your durability, improve your sustainability, and get control over your concrete. That's where we all want to be. When everyone's mixtures are workable, everyone's lives improve. I believe that. This means it's going to be easier to place, drag, consolidate, finish, pump. This means you don't have to adjust mixes on site. This means you don't have to add water to the surface or water to the truck as much, right? So this means aggregates are critical to the performance of your concrete mixtures. Simple tools like the tarantula curve are helpful to help us improve our mixtures. And if we get the aggregates right, then it is easier to control the performance of our concrete. Getting your aggregate gradation right is the very first and most important step, I think, to success when it comes to a concrete mixture. And reducing paste content equals many, many benefits for your concrete. Ladies and gentlemen, I have a YouTube channel. Please, please, please like, subscribe, leave me a comment. I get 10,000 views every day from people around the world about concrete. I am a freak for concrete. Please join the freaks. Subscribe. That's my contact information. Thank you, everybody. I'm over. Please leave comments in the typing chat region. I will do my best to answer those. If I can't do them in person here, I will do them digitally later. Megan can hook me up. I got about 3 minutes before I have to be someplace else. Jagan is coming up next. Jagan is unbelievable. If you think I'm good, you wait for Jagan. He is a gift to the concrete industry. You get ready for this brother. He is amazing. So please don't leave. Just heighten your energy because he's an awesome gentleman. Thank you so much. Thank you so much for having me. I appreciate it.
Thank you, Tyler. That was fantastic. It's just so good to hear you speak about these things. And, I hope we're opening some eyes out there. I always think when I watch this, how do we just implement all this today? And I get frustrated seeing, how long it takes for the industry to change. Do you have any quick tips on how to make this change happen as quick as we can?
Yeah, that's a great question. I think implementation in the concrete world needs to be done with care, right? I wish we could do it tomorrow. I wish we could flip the switch. But I think you'll find some people out there that want to be better. And you need to embrace those people and help those people and get those people engaged. Get these tools, get them using it. Then you've got some people afterwards that will take a little bit more convincing. They're great. They're awesome people. And they just need a little bit more nudging. But I'll tell you what, one thing that's helped in a lot of different states is giving an incentive, is telling people what you want and paying people for what you want. Okay, if you will do those two things, you will blow your mind how your life would change, because our industry wants to do the right thing. Our industry cares deeply, right? But they're not always have the tools to do it. They don't always have the incentive to do it. Let's give them that. Tell them what we want. And I'd love to help you. I'd love to help your state. You've got some amazing people in your state already, and I'd love to do whatever I can to help.
Awesome. Well, I don't see any questions there, and I know you have to run, and we are very thankful that you shared your time with us this morning. And hopefully next time we'll be sitting in front of a nice a buffet and, be able to see you in person. So
that'd be amazing.
Yep. So I'm going to let you run
so much,
here.
everybody.
Take care.
Take care.